So today we're talking about tangents. Now we talked about sine, cosine, and tangent back in chapter 8 and the relationship within the right triangle. But this kind of tangent is different. It's a tangent to a line, to a circle, okay? And it is a line in a plane of a circle that intersects the circle in exactly one point. And that point of intersection is called the point of tangency. So this right here is considered a tangent line. It does not go through a circle, it just goes and intersects the circle in one point. Okay, it kind of just grazes the side of it. The point where it intersects is called the point of tangency. Hard time here. Let's see. Tangency. It's called the point of tangency. All right, and we can have common tangents. And a common tangent is when a line intersects two different circles. So like it can be like circle F and circle G here. This is a common tangent. It intersects circle F here and circle G here. Here you got this one line that's tangent to both circles. They're just kind of side by side here. So that's what a common tangent is. Now we have a theorem, and the theorem states that in a plane, a line is tangent to a circle if and only if it is perpendicular to the radius drawn to the point of tangency. So if this line RT is tangent to circle O, and you draw a radius from O to that point of tangency, then those two lines are perpendicular to each other. Okay? They create a right angle. So, and this is a biconditional statement as well, so the converse of that is also true. If you have a line here that is perpendicular to the radius, then you know that that line is tangent to the circle. Okay? So if you draw a radius to the point of tangency, then you create perpendicular lines. Alright, so with that said, let's work a couple of problems here. It says that ED is tangent to circle F. At point E, we want to find X. Well, if D is tangent to the circle, and then FE is a radius, what's created here at point E? A right angle, okay? And so, if we want to figure out the length of X, what would we do? We would do the Pythagorean theorem, okay? A squared plus B squared equals C squared. Now, what's my hypotenuse? No. X is. Remember, your hypotenuse is across from the right angle. So, we end up with 11 squared plus 7 squared equals x squared. 11 squared is 121. 7 squared is 49. We end up with 170 equals x squared. We take the square root, and if they ask for an exact answer, that would be our exact answer. I don't think that can be simplified. But if they wanted your answer rounded to the nearest tenth, then you would plug that in, 13.0. Okay, here's another one similar to that one. It says JH is tangent to circle G at J, find the value of X. So if JH is tangent to circle G right here, what's created? A right angle, okay? And so then what are we going to do to find X? The Pythagorean theorem, okay? A squared plus B squared equals C squared. Now, what is my hypotenuse? What is it? You have to do X plus A, or A plus X, however you want to write it. Okay, so we're going to do X squared plus 12 squared equals X plus 8 quantity squared. So we end up with X squared plus 144. Now, X plus 8 quantity squared is not X squared plus 64. Okay, remember when you square something, you multiply it by itself. And so what are we going to have to do here? To multiply that, what do? We have to FOIL it. Okay, so X times X is X squared, X times 8 is 8X, 8 times X is 8X, and then 8 times 8 is 64. So we end up with X squared plus 16X plus 64. All right, so our x squareds cancel. We can bring the 64 over, and you end up with 80. And then divide both sides by 16, and so x is 5. Questions on what we did there? Okay, now let's look at the converse of this theorem. We want this time to determine whether MN is tangent to circle L. In the last problem, we knew that it was tangent, so it created a right triangle, and we were able to use the Pythagorean theorem to find the missing part. Well, here, I want to determine if, in fact, this is a tangent, okay? And in order for it to be a tangent, what's this triangle going to have to be? Right triangle, okay? And so we can use the Pythagorean theorem here as well. We know that this leg is 3, this leg is 4. What's the length of this leg going to be? It's going to be 5 because this is a radius here, correct? So this is also a radius, so its length is 3, which means this whole thing here is 5, okay? Ln is 5. And so is this a right triangle? Yes, it's a triple, isn't it? 3, 4, 5. And so my answer would be yes, MN is tangent to circle L. Triangle LMN is a right triangle. Okay, similar question here. It says determine whether PQ is tangent to circle R. We have this leg is 5, this leg is 4. What's the length of my hypotenuse going to be? 8, because this is going to be 4 just like that. So this whole thing here is going to be 8. And so if I did 5 squared plus 4 squared equals 8 squared, 25 plus 16 equals 64. So I end up with 14 equals 64. So is this a right triangle? No. What kind of triangle is it? You look at the longest side. The longest side is 64, right? And that's greater than the sum of the squares of the other two sides. So what is it? Obtuse. Obtuse. Okay, so the answer here is no. Triangle PQR is not right. Therefore, PQ is not a tangent. Okay, so here's another theorem. This one's pretty easy. It says if two segments from the same exterior point are tangent to a circle, then they are congruent. Okay, so if this AB is tangent to the circle and AC is tangent to the circle, they're both tangent from the same exterior point, then this theorem tells us that those two segments are going to be congruent to each other. So if you have two segments from the same exterior point, then those two segments are congruent to each other. All right, so we want to find x. Assume that segments that appear tangent to circles are tangent. So we can make an assumption here that and these two look tangent. Yeah, it's kind of like an ice cream cone, right? You can see that these two are tangent. So since they're both tangent from the same exterior point, what's true about AB and AC? They're congruent to each other, okay? And so I can set negative 2x plus 37 equal to 6x plus 5. And so I add 2x to both sides, subtract 5 from both sides, and then divide both sides by 8, and x is 4. All right, last one. Okay, in this one, it says that triangle ADC is circumscribed about the circular Coca-Cola emblem. Now, when we talked about how to circumscribe a circle about a triangle, in this case, it says the triangle is circumscribed about the circle, okay? That means it encompasses it. And when it encompasses it, that means that each side of the triangle is tangent to the circle. So it only intersects the circle in one point. So CD is tangent to the circle at E, DA is tangent to the circle at F, and CA is tangent to the circle at B. So that's what it means to be circumscribed about a circle. Each side of the triangle is tangent to the circle. okay? And it wants us to find the perimeter of triangle ABC. It also tells us that EC equals DE plus AF, okay? All right, so if, these are tangent, then what's true about DE and DF? They're what? They're equal, okay, so they're both 6. What about FA and BA? They're congruent, so they're both going to be 19, okay? And then EC is made up of DE plus AF. DE is what? 6. AF is 19. Add those together, that means EC is 25. So EC is 25, which means that BC is 25. Good. So now we can find the perimeter, okay? Just add all the pieces together. So we've got 225s, which is 50. We have 2 6s, which is 12, and we have 2 19s, which is 38. Add those together, and you get a perimeter of 100. So, we talked about what a tangent line is. A tangent line intersects the circle in one point. It doesn't go through the circle. It grazes along the side of it and intersects it at one point, and that point is called the point of tangency. A common tangent is one that's tangent to 2 different circles. Okay, what happens if you have a tangent line and you draw the radius to the point of tangency? What happens? They're perpendicular, correct? And vice versa, if you have a line in a diameter or radius or diameter that's perpendicular, then you know that that line is tangent. Okay, and we can use the Pythagorean theorem to find the missing pieces of triangles that are created like that. Also to determine if the line is tangent. Again, we can use the Pythagorean theorem. And then the last thing we learned is what's true about the segments that are tangent to a circle from the same exterior point. They're congruent to each other. Okay. All right. Any questions?